Hi everyone, in this video we are going to practice solving a couple different types of problems that have to do with nuclear energy. So for this course we specifically focus on two different topics, binding energy and mass effect. So for this video specifically, I have three different types of problems that helps us solve each one of those components. So our first problem is talking about tritium, and I give you the mass effect and I want you to actually solve for the binding energy. Go. Alright, did you solve this problem? The first thing we have to do when you see a problem like this is immediately write down Einstein's theory of relativity. So we know E is equal to delta mc squared. So our energy is usually reported in joules. Our delta M is our mass effect. That always has to be in kilojoules. So hint, hint, not AMU. We have to convert our delta M out of AMU into kilograms. And then the last thing we have is C, which is our speed of light. And that's always going to be 3 times 10 to the 8th meters per second. So with these problems, usually you're given energy or mass and we're asking you to convert to the other one. But based on the context of the question, we can make it a lot more complicated than just E equals mc squared where you're solving from one or the other. So you'll see when we get to question 3. But the first thing we're going to do here is convert our mass effect from AMU into kilograms, because we cannot use that number in AMU in the Einstein's theory of relativity. It will not work out. You'll get some crazy number for your energy. So let's start with the first component, which is our delta M, or a mass effect. Now, the problem told us that it's 0.009106 AMU, but they also gave us the conversion from AMU to kilograms. So we can just do this right here. For every 1 AMU, we know it weighs exactly 1.66 times 10 to the negative 27th kilograms. So if you type this into your calculator properly, you should end up with a mass effect equal to something like 1.511 times 10 to the negative 29th kilograms. Okay, so that's step 1. After you have that, it's pretty easy. You just have to put it back into your equation. So we know E is equal to delta M, or your mass effect, which is what we just solved for. So 1.511 times 10 to the negative 29th kilograms, times C, which is our speed of light. That's never going to change. That's a constant. So 3 times 10 to the 8th meters per second squared. Do not forget to square it. A lot of students do that. Don't let that be you. And now all you have to do is plug this in your calculator. So if you do this properly, you end up with an energy of something like 1.36 times 10 to the negative 12 joules. Okay, so negative 12. It's teeny, teeny, tiny. If you solved this and did not have an answer, or did not use your mass effect in kilograms, use AMU, you would have a very, very, very different answer. So just make sure you're always checking the answer. Does it make sense? Is it possible for my energy to be 10 to the negative 12? Yes, absolutely. That's definitely in the right range. This was a job well done. Now let's try number 2. The binding energy of carbon is 5 times 10 to the negative 12th joules. What is the mass effect in AMU? Go. All right, let's work through this one together. So we have E is equal to mc squared. We always start with Einstein's theory of relativity. This time, it's the opposite of the first question. So we're given an energy, and we're solving for our delta M. So I'm going to actually add my delta M in there for you. So now our energy was given to us in joules. We don't have to do anything fancy with that unit. So we have 5 times 10 to the negative 12 joules is equal to our mass effect. That's what we're solving for, times our speed of light, 3 times 10 to the 8th meters per second. That never changes. And then remember to square that. If you do this properly, you solve for your mass effect and get an answer something like 5.55 times 10 to the negative 29 kilograms. So teeny, teeny, tiny. Teeny tiny, okay? So remember this. You need to make sure you have an understanding of what these numbers should be like. Now, the question asks for in AMU, not in kilograms, so we have one more step here. But we're given the conversion right here. We know 1 AMU is equal to a certain number of kilograms. This always will be provided for you. I do not expect you to memorize that conversion. So now we know that we have 1.66 times 10 to the negative 27 kilograms for every 1 AMU. And if you solve this in your calculator properly, you would end up with a mass effect equal to something like 0.0336 AMU. This is an appropriate number for AMU. Something close to 1, but small, it's a decimal, that's a proper number. Hopefully this is making sense. Now we're going to ramp it up one step further. We're going to make it just a little bit harder. So now I want you to do the best you can to solve for this next question. So what is the binding energy for 1 mole of copper 63? Go. All right, were you able to solve this problem? I really hope you were, but who knows? It kind of depends on how much time you spent solving these types of problems. So the first thing you have to do is freak out, okay? Because this type of question has two red flags in it. The first one that I see is AMU. That's bad. We know that we have to get it into kilograms. And the second thing I see is 1 mole. So the 1 mole is going to be the very, very last thing you take care of. The AMU is going to be the very, very first thing you take care of. So let's start off with the AMU component. We know that we have a mass defect that's equal to 0.59223 AMU per every 1 copper nucleus. So what we're going to do is just get rid of that AMU and convert it into kilograms. So now in the previous 2 equations, I provided you with that conversion, so hopefully you have it down by now. We know that 1 AMU is equal to 1.66 times 10 to the negative 27 kilograms. Now, if we solve this properly, we would then end up with a mass defect that's equal to 9.83 times 10 to the negative 28 kilograms per nucleus. So this is for every 1 copper nucleus, all right? So now what we can do is go through and actually solve for our binding energy for 1 copper nucleus. So we're going to use Einstein's theory of relativity. E is equal to delta mc squared. We're looking for our energy, so we can just plug these things in. So energy is equal to delta m. We just solved for that, so 9.83 times 10 to the negative 28 kilograms per copper nucleus, so this is fine, we're just going to leave that unit there, times our speed of light, 3 times 10 to the 8th meters per second squared. Now we can solve for our energy, but we're not done here, so don't just turn the video off. If you do this properly, you end up with a number like 8.85 times 10 to the negative 11th joules per nucleus. So now this is the part where we go back and factor in that 1 mole component. So what is the binding energy for 1 mole of copper? We just solved for it for 1 nucleus. So all you have to do is take it one step further, and hopefully the number that's screaming in your head right now is Avogadro's number, not avocado, Avogadro's number. And so we remember that for every 1 mole, we always have 6.02 times 10 to the 23rd of stuff, of unit, whatever the unit is. And in this case, it's nuclei, or a bunch of nucleuses, which we would say is a nuclei. So if we do this, our nucleus component cancels out, and we're left with an energy of 5.33 times 10 to the 13th joules per mole. Okay, so per 1 mole of copper, we know that we have 5.33 times 10 to the 13th joules. So it's not per nucleus, it's per 1 mole of copper. Hopefully this makes sense. This is as hard as it possibly could be, where we have to convert from AMU and then take care of our nucleus component and convert it into moles. But if you can do this, then you should feel very, very confident that you understand nuclear energy, specifically binding energy and mass effect. All right, that's it for this video. Have a great week, take care of yourself, and drink so much water.